Hello everyone. Today, me and my teammates Vishnu and Deepika, we are presenting about our project today. Information. It's about information retrieval using large language models. It's a RAG approach. The process explores how we can enhance information retrieval in academic settings using the power of large language models. So, what is information retrieval? Information retrieval is the process of finding relevant information from large collections from unstructured data like text documents or web pages. So the goal is to find what the user needs, not just to match the exact keywords like traditional IR systems like index data, rank documents based on relevant scores, and return the best matches. Modern information retrieval goes beyond keyword matching by adding semantic understanding to capture context. Can we go to the next slide? Yeah, so there were can we go back? Yeah. So there were many limitations to traditional informational retrieval that we were using in the past. So traditional search methods often led to information overload and irrelevant results, and the keyword searches can miss the true context, like what the user is exactly needing from that information. So for students like at universities like this FAU, this means difficulty in finding specific information for lecture materials or research content. We wanted to bridge this gap by creating an approach that understands context, not just words, like the true meaning of what our students need. So let's go to the objective of this project. Our goal was to automate the process of answering questions directly from course materials like slides, PDFs, and notes. To achieve this, we built a retrieval augmented generation systems or RAG. In simple terms, the system retrieves the most relevant content and from the slides and then uses large language models to generate context-aware answers. This hybrid approach combines the precision from information retrieval with the intelligence of LLMs. So let's discuss the system architecture based on which our project is. The flow of our system is like a user enters a query, then the slides are split into text chunks, then each chunk is converted into numerical embeddings, and then the embedding are stored in FAISS. It's a vector database. When a query comes in, the retrieval fetches the most relevant chunks, so this final chunks are sent to LLMs, and finally a a contextual answer is generated. So when implemented this using LangChain, FAISS, and OpenAI's API in Google Colab, so this is the whole system architecture based on which our project works. Now over to Vishnu.
Thank you so much, Raghu. And now let's discuss about the methodologies. In our methodologies consists of seven main components. First is the document loader. We use the LangChain to extract text from the PowerPoint slides. And next we use the text splitter. This text splitter is used to the recursive character text splitting that divides the text into manageable chunks of about 800 to 1000 tokens to maintain context. Next, embeddings. The embeddings we use to sentence transformers model all mini LM to generate vector representations of text. And next is the vector store. These embeddings were stored in the FAISS for efficient similarity search. And next is the retriever. We used FAISS as retriever to fetch the most relevant chunks based on the user query. And next is the LLM. We use the open ChatGPT AI to generate the answers. And next is the prompt template. Now I'm going to explain the overview of the code. And in the first step, we have installed all the required libraries is for the code, and then we have we have performed the import function to import all the contents from the Google Drive, and in the next step, we all the slides are extracted actually in the text format from each slide using the LangChain document loader. This step converts all the files into the readable format. Uh, Next, we applied the recursive characters with text splitter, which breaks the extracted text into small chunks of around 500 to 800 tokens with a slight overlap between them. This overlap ensures that the content from one slide flows smoothly into the next, preventing the loss of the meaning during the retrieval. Uh, After splitting editing, we use the Hugging Face transformer model to generate a semantic embeddings for each text chunk. These embeddings are numerical representation that capture the meaning of the text. Now here we can see that all the text chunks are loaded. When, when we then store all the embeddings into the FAISS vector database, which enables fast similarity based retrievals. Uh, when a user asks a question, the FAISS retriever searches the database to find the most relevant chunks of the text from the slides. Uh, the Hugging Face transformer is taking a bit time to load all the data. The Then the retrieved chunks are then passed into the uh, large language model, which uses them to context to generate a clear, accurate, and context answer. To ensure consistency and accuracy, we designed a prompt template that instructs the model to answer the question based on the slides. Uh, in this step, we can see that the LLM is getting ready. We have used an open AI key which we get from the open AI source. Now it printed as the LLM is ready. Now we have the prompt template as I showed you before, and then the finally we created a simple function called ask. Now here we can ask the questions. I'll simply ask the question as what is information retrieval, and then I'll press enter. It processed all the files which I've loaded, and it gave me the answer like information retrieval is finding material of an unstructured data that satisfies an information need from within large collections. And it also gave me the sources from which slide it found the data. And next I'll ask a question like what is cosine similarity. Now it's reading all the files and it gave me the answer and also gave me the source of the file so that it will be helpful for the students and to easily check the notes based on the sources. This is the overview of the slide, and next I'm going to forward this to Deepika, who who will continue this.
Thank you, Vishnu. Now I'm going to tell you about the evaluation matrix, how the evaluation is done. Now let's talk about how we evaluate our system performance. Evaluation is a critical step because it helps us understand not only whether the system works, but how well it performs under real conditions. We focus on three main metrics, that is retrieval accuracy, answer quality, and response time. When it comes to retrieval accuracy, measures how efficiently the retriever identifies relevant slide chunks when a user asks a question. For example, if a student asks, what is information retrieval? Our retriever should fetch the exact portion of the slide that defines IR rather than irrelevant content. We tested this by comparing retriever chunks with the correct slides sections manually and through similarity scores. Now comes to answer quality. And the answer quality was evaluated through manual inspection. We asked several academic questions and analyzed the generated response for clarity, completeness, and alignment with the original slides. Unlike the traditional keyboard-based system that often returns partial answers or irrelevant answers or snippets, our RAG model produced well-structured, context-rich explanation. In simple terms, the model didn't just copy text, it understood the slides and then explained the answer in its own words, just like a teacher teaching assistants would done that. And third one, that is the response time. In this response time, the time between when the question is asked and the answer appears. Even though system involves multiple steps, that is retrieval, embedding, search, and generating, it consistently responds within a few seconds. This is crucial because it keeps the user experience smooth and convenient. From this evaluation, we observe that RAG-based system consistently produces seamlessly accurate answers. Whereas keyboard search often miss the context or return incomplete information. In short, our system demonstrated both speed and seamless precision, making it an effective solution for intelligent academic uh, question and answer. Next slide, please. Now I'm going to tell about the results and observation we have done in this project. So the results, when we move to results and observation, the results clearly showed that our RAG model significantly outperformed traditional information retrieval approaches. Traditional search methods tend to focus on matching words. So if a student's query uses different phrases than what's on the slide, the system might fail or find it. Our RAG system, on the other hand, works at a semantic level. It understands that the question, what does RAG means, is efficiently the same as define what is information retrieval. When we compare side by side example, the difference was evident. The keyboard search results were often fragmented, lack when it comes to the RAG model perform complete natural language answers with accurate context. We also noticed that the response generated by our model were highly aligned with the actual site content. For instance, we tested with questions about system architecture or methodologies. The model directly refers like terms like FAISS, embedded, or chunks exactly as they appear in our slides. This indicates that the retrieval component was working efficiently and that the language model generated answers that stayed grounded in the retriever context. And when it comes to the observation, another observation was the system's contextual understanding. Because the RAG pipeline fit the model with the most relevant slide content, the generated response were not only correct but also explained why recent terms or processes were important. This made the answer more educational and engaging, similar to how a professor would elaborate during a lecture. Next slide, please. Now it comes to the And I want to add some points over here. That is, the challenges we faced during these projects are, while the project was successful, we did encounter several challenges along the way, both technology and practical. The first major issue was API key authentication error. Since we were using the OpenAI API to LangChain, the system requires secure, valid API credentials. In earlier runs, the model accuracy failed to authenticate, leading to connect errors. We resolve this by properly setting up environmental variables in Cloud Collab and generating APIs key when necessary. The second challenges we faced is involve LangChain version changes. LangChain is a rapid evaluation framework and frequent update caused several modules to change or became distract depressed. For example, classes like langchain dot vector stores was shift to langchain underscore community dot vector store, breaking our initial impact. We had to regularly check version logs, update dependencies, and modify our code accordingly to stay compatible. Through time consuming, this process improved our understanding to how LangChain organizes its components. The third challenges and the last challenge we have faced is handling large PowerPoint files. Some lecture slides contains hundreds of lines of text and images, which slow down the text extraction and embedding process. To overcome this, we optimized our workflow by loading slides in batches and catching embedding. This reduces memory usage and improve processing speed. And these are the challenges we have faced while doing our project. And now I want to conclude our project like this, to conclude this project successfully demonstrated how information retrieval can be enhanced using the RAG, that is relevant argument generation framework. By combining the structure relevant power of FAISS with the generative compatible capabilities of OpenAI's language models and integrated them seamlessly through LangChain, we built an intelligent system that can automatically answer academic questions based directly on source materials. The system delivers accurate, context aware, and human like responses, turning static lecture slides into a conventional knowledge source. Through our experiments, we proved that RAG not only improves retrieval precision but also adds depth and conceptual richness to the answers. Sometimes traditional keyword searches cannot achieve. Ultimately, this project highlights the growing potential of large language models in the educational domain, making language more interactive, personalized, and effective. And this is our project, and thank you.